topic 5 is matrix multiplication. So I think we're developing some idea of what it means to multiply a vector by a matrix, and now we'll just look at how we can extend that idea to multiplying two matrices together. So we have a linear system, AX equals B, and now we know how to make these elimination matrices E. So I can make an elimination matrix E. And I know what that's supposed to do. So I want to define matrix multiplication so that the product of E and my coefficient matrix gives me the same coefficient matrix I would get if I did one elimination step. So we know how to do the vector, so I know how to do elimination on the right-hand side now. And I know what effect elimination is going to have on the coefficient matrix, so I want to make sure that whatever definition I come up with for matrix multiplication, it needs to do that. So for a column view, I think of the matrix as composed of n columns. So here, A1, A2, up to AN, these are the columns of the matrix A. And I know how to do matrix times vector multiplication. So I could think of one way I might want to represent matrix multiplication. It's just I'll say the answer needs to be E times the first column of A, E times the second column of A, and then each one of those is going to be a vector, and I'm going to put all those vectors back together in a matrix. And so this would then be the answer to my matrix multiplication product, so my matrix product E times A. Okay. So we have to make this a little bit more rigorous. We have to start thinking of exactly what rules we have to follow. So a matrix is just a rectangular array of numbers. If we say an m by n matrix, we mean that it has m rows and n columns. And I'm going to denote the entries in the matrix by little a ij. So if it has, I'm sort of using the notation here, if it's got one subscript, so if I say just a sub j, that's a whole column. If it's a sub I, that's a row. Or if it's a ij, if it has two subscripts, then that's a particular entry in the matrix. And so that means I can write my matrix A like this. So I have A11 is always the top left entry. Then there's A21 below that, A31 below that, all the way down to AM1. And then for columns, I have A11. Just one step to the right of that is A12, A13, and so on up to A1n. And then the bottom right corner will just be AMN. So this works well for smaller matrices. I suppose if you wanted to actually start talking about, the 13, 17 position, you might want to put a comma in between here. And so for addition, we're going to do addition for matrices just like we did with vectors. So it's going to be, for vectors I called the elements components, and for a matrix I'll call the elements entries, like that. So if two matrices are the same dimension, so they have the same number of rows and the same number of columns, then I can add them, and I'm going to say that the sum is just the element-wise sum. And then I can also multiply a matrix by a scalar value c, and that's going to be the same as a vector. It's just going to be each entry in the matrix multiplied by that value c. So for instance, if I wanted to add these two matrices together, I have in the top left, so the 1, 1 sum is just going to be 1 plus 2, so I get 3. The top right entry is going to be 2 plus 2, 4. And every other one, so this would be 0 plus 9 is equal to 9. And then if I want to multiply by a scalar value c, So here I decided to choose 2 as my scalar value. Then that's going to have the effect of just doubling every element or every entry in the matrix. So 1, 2 becomes 2, 4, 3, 4 becomes 6, 8, and then 0, 0 stays 0, 0. So addition is pretty straightforward. Scaling by a real valued scalar is pretty straightforward. Matrix multiplication we're going to find is a little bit more difficult. So in order to multiply a matrix A by a matrix B, the number of columns of A has to be equal to the number of rows of B. So in particular, if A is an m by n matrix and B is an n by p matrix, then I'm going to have m rows and n columns for A, and then the number of columns of A has to be equal to the number of rows. So I have to have n columns in A and n rows in B. If that's true, then I can make a matrix product. And the output is going to be the dimension of the output, so the dimension of the product, is going to have a number of rows determined by the first element in the product, and a number of columns determined by the second. So the product AB is going to have m rows because A had m rows, and it's going to have p columns because B had p columns. And so one thing you can think of as the matrix form of the dot product is just the most extreme case. So if I have 2 vectors, in this case of length 2, and I take their dot product, I could also write that as U transpose. So that means transpose of a vector just means turn it on its side. So here, U is a column vector. When I transpose it, it becomes a row. So I now have a matrix that has 1 row and 2 columns times a matrix with 2 rows and 1 column. And that's just going to be the standard dot product. And so what was important here was that the number of columns, so in this case 2, and the number of rows, that had to match, and then I'm able to make this product. So this provides a very easy check whenever you're doing any sort of matrix computation. If the dimensions of your matrices don't fit in your products, then you've done something wrong. And so then the rule to find the actual entries in the product AB. So we can say this is going to have the dot product. So I think this is the easiest way. If I'm just interested in calculating the product of 2 matrices, this is the easiest way to think about it. So the entries in the matrix AB are the dot products of the rows of A and the columns of B. So I'm using this notation. So AB is a matrix product. And then I want to take the ith, jth element of that. And the way I'm going to get that, so that's going to be one single number. And remember, dot products give me a scalar value, which is one single number. The way I'm going to figure out what that number is I'm going to take the ith row of A and take the dot product of that and the jth column of B. And then once I know what the dimensions are, I'll know what the ranges of I and j are. And then I just have to fill in the matrix one by one. You can also write this out using a sum notation. So here, just instead of writing AB, I'm going to call that matrix C. So C is the product of the matrix A and B. And then C sub ij are the entries of that matrix. And this is basically just writing out exactly the same operation that this would be doing. So here I'm summing over k, so k is the thing that's changing. So this I here is the same for all n of the pieces of this sum. And similarly, j is staying the same. So it means that the row of the matrix A that I'm looking at is determined just by the position of C in the answer. And then I'm going across the row and down the column to compute the actual value for that entry C. And so, for example, you can just do a quick 2x2 example. So if I want to know where this 5 came from, this 5 is in the 1, 1 position. So that tells me it's the dot product of the first row of A and the first column of B. So that would be 1 times 2 plus 1 times 3, which gives me 5. Or I can look at Cij, so C11. So this number here would be C11, would be A11 times B11 plus A12 times B12, which is exactly the same thing. Oops, sorry, B21. So A11, B11, A21, sorry, A12, B21, which gives me the same dot product. So I find it tricky to keep track of all these subscripts, as you just witnessed. So I prefer thinking of it like this, or more likely using a computer to calculate these things for me. And one thing to keep in mind, so for 2x2 and 3x3 cases, generally it seems pretty straightforward, but really what you're aiming at is solving much bigger systems of equations. So you want to think about how much work it's actually going to take. So now again you have a computer, so it's not so bad. At least it's not you doing the work. But imagine if you had to solve a problem on a chalkboard. You would have really two considerations. One is going to be how many different operations am I going to need to do? So for each cell in this matrix, so this one is, if it's a 2x2 matrix, there's going to be 4 cells. I need to do n multiplications, so that's just my dot product. And then to add those up, I need to do n minus 1 additions. And then there's going to be, so in this case it's square, so it's n times n. So this algorithm, I'm going to have to do something that takes 2n roughly steps, and I'm going to have to do that n times n times. So it's going to take 2 times n cubed mathematical operations, like simple mathematical operations, for me to do this matrix product. And so the other consideration you might want to think is how much memory is that going to take? So if I were doing this on a chalkboard or on a piece of paper, the chalkboard's nice because I can actually reuse parts of it by erasing a number I don't need anymore and writing another number in that space. A little bit more difficult to do with a piece of paper. Surprisingly, if you're programming a computer, generally when you want to optimize an algorithm, you're doing pretty much the same thing. You want to use the least amount of memory and do the least amount of mathematics. So a lot of what was developed initially when people were trying to solve these problems by hand is still really quite useful for solving them with computers. Okay, so an inner product is a row times a column. So this was the example I gave of a dot product being a simple example of matrix multiplication. So if I have a row times a column, then there's only going to be, so that's one row with several columns times one column with several rows. So the answer is going to be a scalar. I can actually move those or do that in the opposite order. So now I can do a single so a matrix that's a single column times a matrix that's a single row, and that gives me something called an outer product. And this outer product is now going to be a matrix. So I have a 3x1 matrix times a 1x3 matrix, and so it's that 3 on the outside and so at the beginning and the 3 at the end. They give me the dimension of the answer. And then the ones that have to match up on the inside so I can actually do the matrix multiplication. So an inner product gives me a scalar value. An outer product gives me a matrix like this. Then some useful facts about matrix multiplication. So each column of AB is a linear combination of the columns of A. So if I look at A times a column of B, this is exactly the same thing I was doing when I was multiplying a matrix times a vector. And I said that I could interpret that using my column picture as a linear combination of the columns of A. And so that gives me each column of the product is going to be a linear combination of the columns of A. And then I can get a similar result. So the rows of the product, so the row I of AB, the rows of the product, are going to be linear combinations of the rows of B. So here, this is sort of how I want to think about it. I take one row of I, and that's, or sorry, one row of A, and that's going to give me the coefficients for the rows of B that give me row I of AB. And so then laws for matrix operations, we get a commutative law. So for addition, we have A plus B is equal to B plus A, and you can show that just with the same argument I did for vectors because it's defined entry-wise. I get a distributive law. So if I take the sum of A plus B and scale that by a scalar value C, then that's equal to A scaled by that constant and plus B scaled by the same constant. I get an associative law for addition, so it doesn't matter if I want to add A plus B plus C. I can add B plus C first, or I can add A plus B first. I'm going to get the same answer. For multiplication, it's a little bit trickier. So I get a left distributive law. So if I have C times A plus B, that's equal to C times A plus C times B. I get a right distributive law. So A plus B times C is equal to AC plus BC. And the important thing to keep track of here is if C comes first, it has to always come first when I'm doing this distributive operation. If the A and B come first, then the A and B have to come first when I'm doing this distributive operation. And then I also get an associative law. So if I want to calculate the product of three matrices, A times B times C, they have to be the right dimensions. So the number of columns of A has to equal the number of rows of B, and the number of rows of B has to equal the number of columns of B has to equal the number of rows of C. I think I got that right. But if I can do those operations, then it doesn't matter what order I do them in. So I can do the product BC first and then multiply that by A, or I can do the product AB first and multiply that by C. So one law we don't get is a commutative law for matrix multiplication. So almost all the time, A times B is not even equal to B times A. And it's even worse than that. So if P is not equal to M, so remember A is an M by N matrix, and B is an N by P matrix. If P is not equal to M, then I can't even do this operation, because the dimensions won't line up when I switch the order. If both A and B are M by N matrices, if A is M by N and B is N by M, then if I do the product AB, I'm going to end up using these outer dimensions. When I do the product BA, now the outer dimensions are going to be N and N. So AB is an M by M matrix. BA is an N by N matrix. So these things, they can't be equal to one another if they have different dimensions. So for equality, they have to be the same dimension, and then each entry has to be equal. And then when we have square matrices, so if we have N by N matrices, at least I can do the products, and they'll be the right size. But suppose I let A equal 0, 0, 1, 0, and B equals 0, 1, 0, 0. So if I do this product AB, that gives me 0, 0, 0, 1. But if I do the product BA, I get 1, 0, 0, 1. So even when I can do it and they're the right size, you're still not guaranteed to get the same answer if I do the multiplication in the opposite order. So one exception to this rule. So this is a constant C, a scalar value. And this is the identity matrix. Yeah, it's kind of hard to see with this font. So one matrix that always commutes is the identity matrix. And so if it's scaled by a constant value, that will also commute. So if you have an identity matrix times something and they're square, then you can switch the order of that multiplication. And then one more thing that I want to mention, just because I don't know really where else it fits in, matrix powers. So a power of a matrix, if I talk about A squared, A needs to have the right dimension, so basically it needs to be a square matrix. If I have A squared times, say, A cubed, that's equal to A to the 5th power. So these behave just like numbers would. And if I have, say, A squared and that quantity cubed, that's equal to A to the 6th. And then if I talk about A to the 0, that's going to be equal to 1, and 1, when I'm talking about matrices, is the identity matrix.
Did you say that A had to be a square matrix for that to work? I was right?
Well, because you can only multiply A by A if it has the same number of rows and columns, so that means it has to be square. Okay. Then I can also do something called putting a matrix into block form. So here I have a matrix with 4 rows and 6 columns. And then I'm going to break it into 6 blocks, and each block is going to be a 2 by 2 identity matrix. So I could also write A like this. So these are just 6 identity matrices. They're all 2 by 2. And then if I make these blocks the correct size, I can do block multiplication following the same rules that I would do for matrix multiplication. So if I have a matrix A that I can split into 4 blocks like this, then when I want to figure out what the product of this matrix is, I can do the product blockwise. So I just pretend like these are values. It would be A11 times B11 plus A12 times B21, which is exactly what I end up with here. So it's the same formula for matrices, except now I'm talking about blocks of matrices, or sorry, blocks, which are kind of sub-matrices of a matrix. And the only caveat here is you have to define your blocks so that all of these operations are permitted. And the reason I want to do this is it lets me do one last clever thing, which I can also now define matrix multiplication in terms of columns. So I can get a sort of a column space. So my first definition was rows of A times columns of B. If I make my blocks the columns of A and the rows of B, and then I use this rule here, what I end up with is a column of A times a row of B. But if I have a column times a row, that was an outer product. So that's actually a matrix. And it turns out that what I end up with are n matrices. So here, AI, BI is an outer product, so that's a matrix. I have n matrices like this, one from each row column or column row combination here. And then I add up those n matrices, and that will also give me this product AB.